As I was saying, the enolate reacts with chlorine. These electrons attack chlorine and kick off the other. Okay? That gives what? Okay? Forget about that. That's resonance going that way. This is your chemistry. What do we get? Chlorine is now bonded here, plus what? Cl minus. And there you go. There's a monohalogenation. It comes from just making your enolate and then it attacking here. But it's the carbanion form of the enolate. Questions?
Now, when you're going to repeat this, you can't use that Cl minus, right? Because you have to have, like, you're just going to make another anion, and an anion won't attack minus because they repel.
No, we're using excess base. Cl minus is not strong enough to make a anion, enolate enolate.
It's going to take another H, isn't it?
Right. We're going to basically repeat the process. This H is here. We're going to come in here with hydroxide and make another anion. We're basically repeating the process. This gives Cl minus here, and there's your enolate. That looks nothing like an enolate. That's because I'm not showing you the resonance structure with the double bond here. Okay? But because it reacts on carbon, I'm often not going to show you that resonance structure. We're actually going to work from the minor resonance structure. But it's called enolate. You very rarely get the oxygen of your enolate reacting. But it's much more favorable to have your product have the ketone or the carbonyl. There's some unique reactions where the oxygen will react, and you can basically get a product like this with something on the O. But most of what we're going to do is the carbanion is going to react. What do? We come in with the other equivalent of chlorine, and it does it again. And when it does it again, what do you get? You get a product. Plus 2 Cl minuses. And of course, the 2 sodium sit with the Cl minuses. 2 sodium cations, ions. Now, again, you can't stop here. Hard to stop here. Monohalogenation, we have to. Can you chlorinate again? Can you halogenate again?
Yes.
Not there.
Not there, but those H's are not acidic. That would be a non-stabilized carbanion, and those are very difficult to make. You're not going to make those with hydroxide. H's on the benzene ring are not acidic. The only acidic H's are the ones that make alpha. Or, if there's resonance to essentially make other H's acidic because of resonance. And that actually goes back to this one over here. Let's finish up this first and we'll go back to the first page. What else can we say here? Why is it hard to stop there? Where are we at? Pull down a little bit. Again, under acidic conditions, you can stop with adding just one. Let's look at this. Why is it hard to stop there?
Because since its H's are acidic, obviously the base wants to take the H's.
Yeah, but you could say the same thing for enol. I mean, this could form an enol under acidic conditions, and you could do it again. Why does it not? Why does the enol not chlorinate again? Why does this one? Basically, what you should take from this, since it's hard to stop here, what this means is putting the second one on is actually easier than putting the first one on. The only way you can stop here is if this was difficult. If this was more difficult, then you could sort of build this up and you could get okay? But here, actually, this is easier. So what happens is as soon as you make some of this, it puts the second one on. And you can never get a good yield of this. And if you only use one equivalent of chlorine, you'll get a mixture of both. You got to just go ahead and do what it wants to do. Why is it easier? It's easier because which is more acidic? That or this? Why? Well, let's look at where we're going. Which is more stable? This anion or the anion over there? They both have resonance in the carbonyl, but what does this one have in addition? It's not resonance, it's just induction. The chlorine pooling stabilizes that anion. And what happens is it makes enolate formation from this guy faster than from this guy. So as soon as one molecule of this is formed, it won't just sit there and, okay, I'm not going to go again. The second one goes on just faster. Because enolate formation is your rate determining step. Forming the anion is your rate determining step.
But with the acid, since that's a plus there, that's why it's.
No, it's not a plus there. You have to look back at it. Why the acid doesn't work is actually a more difficult discussion. You can rationalize it, but you have to look at it closer. Under basic conditions, we do exhaustive. Okay. Now, let's look back at something over here. There's a question over here. How many tautomers are possible? I actually want to ask another question about this. First off, how many tautomers are possible? I heard of 1, a 4, 2, and then I heard of 3. First two? How many tautomers? 3. Answer is 3. Okay? The answer is 3. Okay? Does anybody know why? Can you draw all 3 of them? Okay? Please draw all 3 and we'll look at it next time. What's going on here is because of those alkene double bonds, you can have resonance sort of in between. What you can have here is, we only make anion next to carbonyl, but you can also essentially put a double bond in between. Now you can make anion here. Because now you can make anion here, and that's conjugated with the carbonyl. It's conjugated via the alkene. Because now we can draw resonance structures like this and put anion here. Then we can keep going, okay? This is called a vinylogous anion. Because an alkene, a slang for alkene is vinyl. I've never spelled this. Vinylogous. Basically, the vinyl group makes this acidic because it links it with the carbonyl. And if you do your Oreo under basic conditions, which is easy to just visualize an enol formation to me, you can see. So the other question I could ask is, how many acidic CH sites are there? Those H's are acidic. I'll call that one site, although there's 2 H's here. How many carbons in this molecule have acidic H's? 3. H's on that carbon are acidic enough. Where else?
The one on the other side.
There, there, and there. Is this H acidic? Not acidic in terms of none of them are acidic. Okay, again, these CHs are not called acids. They're acidic enough to do chemistry. Okay, that's not putting anion there. That would not be resonance stabilized. That's a good structural thing to be looking at. That H is not acidic. You cannot do any resonance. Put an anion there, you cannot do resonance with that. That lone pair is actually in a hybrid orbital. It's a good structural thing to think about. Okay? In the end, these H's we can do the enolate chemistry with because this double bond is going to link the anion to the carbonyl. Exhaustive, okay? Let's show the product of this here with bromination. Go ahead and show that. How we do? You have two acidic H's on the right. Don't forget that the other side may have acidic H's. Okay? We're going to deprotonate and brominate 3 times. You're going to have to use how many equivalents of bromine to get that product? You need 3 equivalents of that. You also need 3 equivalents of base, because actually the base is not reformed under basic conditions. Under acidic conditions, the acid is a catalyst. When you halogenate under basic conditions, it's not. Because at the end, we're going to have what if we balance this out? We're not balancing. We're going to have sodium bromide. How many equivalents? Yeah. And when we say equivalents, this is basically like balancing it. You need 3, 3, 3. You get 1 of these, 3 of these. Okay, haloform reaction. Questions about that one up there? Haloform reaction. One of the top 10 reactions in organic chemistry. It doesn't have a person's name. It's named describing the chemistry. It's an important reaction. It's unique, but when we look at the mechanism, it'll be pretty straightforward. What happens here? It's a conversion of methyl ketones to carboxylic acids. Methyl ketone. And essentially, the methyl is replaced with the OH, and we get carboxylic acid. Importantly, the byproduct is going to be HCX3. If you use chlorine, this would be HCCl3. What's the name of this molecule? Haloform. Haloform. You could have said trichloromethane, and you would have also been right. But nobody calls it trichloromethane. Chloroform. If it was Br, it would be called bromoform. Iodoform. Okay. Chloroform is a liquid. It's a solvent in the lab. A little bit toxic. Deuterated chloroform is a common NMR solvent. It's used during like World War I, Civil War, back in then, to knock people out. Queen Elizabeth inhaled it to give birth, not Queen Elizabeth, Queen Victoria. Chloroform, okay? In general, it's called a haloform, halogen, okay? So this reaction produces a haloform. But that's sort of the byproducts. This is more of the, the major organic product. What's going on here? The first step is what's going to happen? We just covered this.
Add three.
First step is exhaustive halogenation. Okay. This can be eye done. We'll talk about this. The first step is to get let's say we're using bromine, okay, instead of X, so I can put bromine. You put 3 bromines on your carbon. Now, there's actually more to the first step, because I see that this is just working up. At this point, you still have hydroxide, because we're using excess. Now, this would consume 3 equivalents of hydroxide, which are using even more than 3. At this point, the hydroxide, there's no longer acidic H. Even if they're wet, you can still do this, even if they're wet. Now the hydroxide adds to the carbonyl electrons up. Nucleophilic addition to carbonyl. Now what happens next? Can you see it?
Electrons down.
Electrons down, and what do we kick off?
BR3.
We're actually kicking off a carbon. But anytime you can make a pi bond and kick off a leaving group, this is pretty easy to do. Now we said you don't kick off plain carbons or plain hydrogens. But what are we kicking off here? What do we get? This is going to give this with the OH now, plus what? Plus this. Is this an ordinary carbon or carbonide, or is it stabilized somehow?
Stabilized.
Yes, it's stabilized by the 3 bromines. And apparently that's why it will leave. And essentially you're doing like acid derivative chemistry, addition, elimination, acyl substitution. And if you look back when I introduced acid derivative chemistry, and we said how more things can leave other than SN1, SN2, I said even carbon can leave sometimes. And I said haloform reaction. That was about 4 or 5 handouts ago. Okay? Haloform reaction. Now, what happens next? This is still a carbanion. This is an acid. What happens next is this takes the H. Leaves us behind. That's going to give O minus plus HCBr3. That's bromoform. This is in step 1. How do we get the final product? You got to throw in your favorite strong acid, HCl, etc. I'm not even going to do mechanism, okay? Anion takes the H+, you got to protonate it. And essentially, we replace the methyl with an OH. Exhaustive halogenation. Now, back up here. Why did hydroxide not add here and kick off this carbon? I mean, it's got two halogens on it. Well, here it is. The carbon will only leave to produce the carbanion if there's 3 halogens on it. I mean, this is what Mother Nature gave us. Only 2 and it will not leave. But with 3 it will. And it does. There.
The end methyl group there on the end of that chain for the 3 H's, with all that induction pooling, would any one of those H's become acidic enough to replace normal in the next sequence?
Replace what?
The H's on the very end of that chain there.
You mean here?
Right.
No. They're more acidic than if the chlorines were not there. but they're still not acidic to do any chemistry with. Definitely not in this class.
I won't be taking organic theory, by the way.
Okay.
That's not a
You won't see that in there. Anytime you get an electronegative heteroatom in a molecule, it's always going to slightly increase the acidity. But the question is it enough to actually do chemistry with in a practical manner? And not in this case. Okay, any questions? Thus, the only way you're going to kick off this carbon is to get 3 halogens on. The only way to get 3 halogens on is to start with what? 3 H's. Thus, the only way to have 3 H's is that just to be a methyl. There's a couple of tricky or roundabout ways to get 3 H's on, 3 halogens on. In the end, if you can get 3 halogens on, then this chemistry can take place. And it's a roundabout sort of ingenious way to make a carboxylic acid from a methyl ketone. For example, well, let's go back and review. How would you make this from benzene? It's actually a synthesis of benzoic acid. If you had benzene, how would you first make this?
Seal crabs, isolation.
Yeah. Then you can sort of do your haloform reaction and get that methyl replaced with an OH. Or to get the carboxylic acid, what do we do? Maybe you brominate and make bromobenzene. Then how could you convert this to a carboxylic acid? Make Grignard react to CO2. Or you could put a big alkyl chain on and then oxidize it off with KMNO4. You remember how that chews it off? Okay. So basically we're getting to how you can make a given functional group a variety of ways. The haloform is actually used as a chemical test with iodine. And it's called the iodoform test. A methyl ketone will give a precipitate of iodoform. See, iodoform is actually a solid, where chloroform and bromoform are liquids. And since it's a solid, it's sort of a yellow, it's a somewhat gelatinous solid, but it's a solid. If the chemistry takes place, and you get your iodoform form, it will typically precipitate, and thus that's a visual evidence. You can see the precipitate form. But of course, you only get the byproduct iodoform form if your starting product had what? Methyl ketone. So these isomers here, which are going to give very similar NORs, very similar IRs. Now mass spec would be different. Mass spec would be significantly different. But we can also perhaps distinguish them by using an iodoform test. Which one would give a positive iodoform test?
Far right.
Obviously this one, because it's the methyl ketone. This one, you will put 2 iodines here when you treat it with hydroxide and iodine. But it's not going to get cleaved off and produce the yellow precipitate of iodoform. So that's a chemical test. About the 4th or 5th one we've seen this lesson. Questions about exhaustive halogenation or iodoform tests? Let me finish by doing this here, and let's introduce next. Next, we're going to be putting things other than halogen on, deuterium. Then we'll be looking at putting carbon on. For example, putting another carbon on this carbon. And when you add carbons, that will be called alkylation. We're going to put alkyl groups. Please be looking at that. Why is it good to put halogens on? What can you do with it? Well, remember, if we can put a halogen on, In this case here, I'm putting it on with acidic conditions, so I can just put one on. What can you do with this? Keep in mind, now we have a halogen, and we can do all that leaving group chemistry, like SN1, SN2. We treat it with this, what are we going to get? Show product. We can do other things. Please look ahead. See you in labs. Oh, yeah, guys, there is a seminar this week on Friday at 1 o'clock. It's someone from UGA. It's cancer. They're talking about prostate cancer and diet. How high fat, I think, may promote prostate cancer. And they're talking about science and how and why. Friday at 1 o'clock if you'd like to come. Have a good week, guys.